Come for physics lesson. We're going to revise paper 1, section 1. A few questions here. And the first one is from the moments of a force and equilibrium and center of gravity. A figure below shows a uniform meter rule pivoted at the 23 centimeter mark. So it's pivoted at the 23 centimeter mark with a mass of 3.6 kilogram hanging at the 0 centimeter mark. The system is in equilibrium. So if the system is in equilibrium and the pivot is not at the center, then the weight of the object should be acting downwards through the center. So the weight, which is unknown, is acting through the center. The center is the 50 centimeter mark because it is 100 centimeters long. Determine the weight of the meter rule. So we consider moments here, and you say that sum of clockwise moments should be equal to sum of the anti-clockwise moments. Therefore, the only clockwise moments here are moments due to the weight, which is a known W, multiplied by a distance of from the point of support to 50. The point of support is already at 23. So from there, we will have 27. Because they are centimeters, we make them SI units. These moments should be equal to the moments due to the anti-clockwise force. And we make it force by multiplying with G. So instead of 3.6 kilograms, we use 36 Newton. So 36 Newton times a distance of 23 out of 100, because it is 23 from the point of support. Therefore, here we can get weight by dividing 36 by 23. We divide with 27. This gives us 30.67 Newton. So that is the weight of the meter rule. The normal reaction force at the rule. So here we will talk of upward forces should be equal to downward forces. Therefore, we have two downward forces, the mass of 3.6 and the weight of the rule. Therefore, we will add, to get upward forces, which is the reaction, we will add all the downward forces, 36 and 30.67. This should give us 66.67 Newton. That will be the downward forces, which are equal to the upward forces, and the only upward force is the reaction at the pivot. Then we're given another question here which says, when mercury in a glass thermometer is used to measure the temperature of hot water, it is observed that mercury level first drops before beginning to rise. So this is mercury inside a glass. Mercury inside a glass. Then we are saying that when it is used to measure the temperature of hot water. So when we immerse this one in hot water, the column of mercury first drops before beginning to rise. And the point is because the glass absorbs heat first. The glass absorbs heat and expands fast. Creating a larger volume. Then now later, the mercury absorbs heat. So later, heat reaches the mercury, which also expands. At a faster rate than glass. So now we will see it rise, not because the glass is not expanding now, but because mercury finally gets it and starts expanding at a faster rate than the glass is. Then we got another question here from collisions. You know, the law of conservation of energy, or the law of conservation of linear momentum, whereby we are told a trolley of mass 0.5 moving with a velocity of 1.2 collides with a second trolley of mass 1.5 moving in the opposite direction with a velocity of 0.2 meters per second. If the collision is inelastic, inelastic means they collide and combine and move together with a common velocity. Determine the velocity of the trolleys after collision. Therefore, here we say momentum is conserved, and momentum before collision should be equal to momentum after collision. Momentum after collision. Therefore, the point is mass 1 and velocity 1 plus mass 2 and velocity 2 should be equal to the combined masses with the new unknown velocity now. Therefore, the first mass is 0.5, velocity 1.2, and we add the second mass is 1.5 and a velocity in the opposite direction, which is 0.2. So this one must be treated with a negative because it is going opposite to the other mass. Then we will have a mass of 0.5 plus that of 1.5 times a new unknown velocity. So here we will talk of 0.5 multiplied with 1.2, which is 0.6. Then we subtract 1.5 multiplied by 0.2, and this gives us negative 0.3 equals to, this becomes 2.0 by v. 2.0 by v. So to remain with velocity, then we can divide this by 2 and we'll get negative 0.15 meters per second. This means after collision, the trolleys will move with a common velocity of 0.15 meters per second to the direction of the second trolley. To the direction of the second trolley. So it should be noted that a negative here does not mean a value below 0, but means a velocity in the direction at which we gave to the second trolley. So if finally we are getting a negative velocity and it is the second trolley which had a negative velocity, then it means they are moving to that direction. In case we had a positive, they could be moving to the direction of the first trolley. A block of copper of mass 2 kilogram and specific heat capacity 400 joules per kilogram per Kelvin, initially at 81 degrees Celsius, is immersed in a water at 20 degrees Celsius. The final temperature is 21. Determine the mass of water. So what we should know here is that heat lost equals to heat gained, and a block of copper is the one losing heat because it is at 81 and water is at 20. So heat lost by copper should be equal to heat gained by water, because it is water which is gaining now. We have only two components here: water losing heat, water gaining heat, and copper losing it. So we will say now, assuming that there are no heat losses to the surrounding, mass of copper, which is 2, times specific heat capacity of copper. Specific heat capacity of copper is already given, times change in temperature. All the way from 81 to 21, we are getting a change of 60. This should be equal to the mass of water unknown times change in temperature, which is from 20 to 21. So this is by 1 times specific heat capacity of water, which is 4200. We are supposed to get the same heat. So the heat which has been gained by water, assuming there are no heat losses to the surrounding, should be equal to the same heat that was lost on the other side by copper. And we can now get 2 by 400 by 60. Then we divide with 4200. So that we may say the mass of water was, this is M now, M equals to 11.43 kilograms. So the mass of water was 11.43 kilograms. Thank you for following. Subscribe to this channel and share the link.